Welcome! In this session, we'll explore an interesting coding problem: number of equivalent domino pairs. Together, we'll break down the problem, analyze different approaches, and understand the optimal solution. Let's dive in. In this problem, we are working with a list of dominoes, where each domino is represented as a pair of integers, a, b. Two dominoes are considered equivalent if they have the same numbers either in the same order or in reverse order. For example, the domino 2, 5 is equivalent to 5, 2 because the numbers match when reversed. However, 2, 5 is not equivalent to 3, 4 because the numbers are completely different. The goal is to count how many pairs of dominoes in the input list are equivalent based on this rule. To clarify, we are looking for pairs of indices I, j, such that 0 equals I less than j less than n and the domino at index I is equivalent to the domino at index j. The input will be a list of these dominoes, and the output will be a single integer representing the total number of such equivalent pairs. Let's look at an example to better understand the problem. Suppose the input list of dominoes is 1, 2, 2, 1, 3, 4, 5, 6. The output for this case is 1. Here's why: the first domino, 1, 2, is equivalent to the second domino, 2, 1, because the values match when reversed. This forms one equivalent pair. The other dominoes, 3, 4, and 5, 6, do not have any equivalent pairs in the list, as their values do not match any other domino. Therefore, the total number of equivalent pairs in this example is 1. Now consider another example where the input is 1, 2, 2, 1, 1, 2, 2, 1, 3, 4. The output here is 6. Let's break it down. Dominoes 1, 2, and 2, 1 are equivalent and they form multiple pairs. Specifically, the pairs are as follows: domino 0 with domino 1, domino 0 with domino 2, domino 0 with domino 3, domino 1 with domino 2, domino 1 with domino 3, and finally domino 2 with domino 3. The domino 3, 4 does not have any equivalent pairs, so it is not included in the count. Summing up all these valid pairs gives us a total of 6 equivalent pairs. Let's discuss the constraints and their implications for solving the problem. The input list can have up to 10⁻4 dominoes, which means we need to ensure our solution is efficient and can handle a large number of elements. Each domino consists of exactly 2 integers, both of which are between 1 and 9. This means there are at most 81 unique domino configurations, considering all possible combinations of 2 numbers and their reversals. Since both A, B, and B, A are treated as equivalent, we need to carefully account for this symmetry when identifying pairs. Finally, some edge cases to consider include a single domino in the input, where no pairs are possible, and situations where all dominoes are distinct, which would also result in 0 equivalent pairs. Let's look at a few more edge cases to reinforce our understanding. In the case where all dominoes are identical, for example, 1, 2, 1, 2, 1, 2, the output is 3 because every domino forms a valid pair with each of the others. Specifically, we have pairs 0, 1, 0, 2, and 1, 2. Another interesting case is when the dominoes are reverse equivalent, such as 1, 2, 2, 1, 1, 2. Here, domino 1, 2, and 2, 1 are equivalent, and the valid pairs are 0, 1, 0, 2, and 1, 2, resulting in an output of 3. These examples highlight the importance of considering both the order and the reversal of values when determining equivalence. To solve the problem of counting equivalent domino pairs, we first consider the brute force approach. This involves comparing all pairs of dominoes to check if they are equivalent. A domino is equivalent to another if it matches either in the original order, like A, B, or in the reversed order, B, A. The steps for this approach are straightforward. Use 2 nested loops to iterate through all possible pairs of dominoes, check the equivalence condition for each pair, and increment a counter whenever you find a match. However, this method has significant limitations. Since we are checking all pairs, the time complexity is n squared, which becomes impractical for larger inputs when the number of dominoes, n, approaches 10,000. Additionally, it doesn't use any additional space, so the space complexity remains 1. While simple to implement, this approach is inefficient and not ideal for scenarios where performance is critical, such as competitive programming or large-scale data processing. To address the inefficiencies of the brute force method, we adopt an optimized approach using hashing. The key insight here is that the order of the domino values does not matter when determining equivalence. Instead, we can represent each domino uniquely by arranging its values such that the smaller number comes first. For example, both 2, 5 and 5, 2 are represented as 2, 5. Using this representation, we can count equivalent pairs efficiently by leveraging a hash map. The hash map stores the frequency of each unique domino representation. As we iterate over the dominoes, we calculate their canonical form, update their frequency in the hash map, and use the formula count** count 1 //2 to compute the number of equivalent pairs for each unique domino. This approach ensures that we only traverse the domino list and the hash map once, making it significantly faster. The time complexity is reduced to O(n), as sorting each domino and updating the hash map is constant time, and the space complexity is O(n) to store the hash map. This method is highly efficient and scales well for larger inputs. Here's how the implementation works in code. First, we initialize a hash map to track the frequency of each unique domino representation. Then, as we iterate through the dominoes, we compute the sorted representation of each domino using min, a, b, and max, a, b, to ensure the smaller value always comes first. We use this representation as the key for our hash map. For each domino, we add the current frequency of its representation to the result, and then increment the frequency in the hash map. At the end of the iteration, the result contains the total number of equivalent pairs. The key realization here is that by consistently representing each domino in its canonical form, we eliminate the need to compare all pairs directly. Instead, we rely on the hash map to handle counting and aggregation efficiently. This simplifies the problem from a computational perspective, making the solution both elegant and performant. When comparing the two approaches, the brute force method is simpler to implement but inefficient for large datasets due to its O(n)² time complexity. In contrast, the optimized hashing approach is slightly more complex but offers significant improvements in performance, especially for larger inputs. By reducing the runtime to O(n) and leveraging a hash map for constant time lookups and updates, this method is far more scalable and practical for the given constraints. The choice is clear: the hashing approach is the better solution for this problem. It balances efficiency, scalability, and simplicity, making it ideal for competitive programming and real-world applications where performance is critical. The problem asks us to determine how many pairs of dominoes in a given list are equivalent. Each domino is represented as a pair of integers, a, b, and two dominoes are considered equivalent if their numbers match either in the same order or reversed. To solve this, the brute force approach involves systematically comparing every pair of dominoes for equivalence. First, we start with the input list of dominoes and initialize a counter variable to keep track of the number of equivalent pairs. Then, we use two nested loops, an outer loop that iterates through each domino and an inner loop that compares it with every subsequent domino in the list. This ensures that we check all possible pairs without double counting. The goal is to identify which pairs satisfy the equivalence conditions and update the counter accordingly. In the brute force approach, for each pair of dominoes, we check if the two dominoes are equivalent. Specifically, we examine if the first domino matches the second either in the same order, where A == C and B == D, or in reversed order, where A == D and B == C. If either condition is satisfied, we increment the counter by 1. Once all possible pairs of dominoes have been checked, the value of the counter represents the total number of equivalent domino pairs, which we return as the result. For example, given the input 1, 2, 2, 1, 3, 4, 4, 3, we initialize the counter at 0 and compare each pair of dominoes. We find that 1, 2, and 2, 1 are equivalent in reversed order, so we increment the counter to 1. Similarly, 3, 4, and 4, 3 are also equivalent, bringing the counter to 2. The final result is a total of 2 equivalent pairs. This brute force approach has a time complexity of O(n)², because we use two nested loops to compare all pairs of dominoes. While simple to implement, this quadratic complexity becomes inefficient for larger input sizes, such as when the number of dominoes exceeds 10,000. On the other hand, the space complexity is O(1), as no additional data structures are used beyond the input list and the counter variable. To address the inefficiency of the brute force method, we can use an optimized approach with a hash map. The key idea is to normalize each domino, ensuring that the smaller number always comes first. For example, 2, 1 is normalized to 1, 2. By storing the frequency of each normalized domino in a hash map, we can efficiently count equivalent pairs without needing nested loops. This drastically reduces computation time. In the optimized approach, after normalizing each domino, we use a hash map to track the frequency of each normalized representation. For every new domino, we check how many times its normalized form has already been encountered in the hash map. The count of these prior occurrences gives the number of equivalent pairs for that domino, which we add to the total count. We then update the hash map to include the new domino. For example, given the input 1, 2, 2, 1, 3, 4, 4, 3, we normalize the dominoes to 1, 2, 1, 2, 3, 4, 3, 4. As we process each domino, we find that the second occurrence of 1, 2 contributes one pair, and the second occurrence of 3, 4 contributes another. The total count of equivalent pairs is 2. By leveraging the hash map, we avoid redundant comparisons and achieve a more efficient solution. The hash map is the key data structure in the optimized approach, allowing us to efficiently store and retrieve the frequency of normalized domino representations. This eliminates the need for nested loops, reducing the time complexity to O(n), where n is the number of dominoes. The space complexity is O(u), where u is the number of unique normalized domino representations. This approach handles various edge cases effectively. For example, if all dominoes are unique, such as 1, 2, 3, 4, 5, 6, the result is 0 pairs. If all dominoes are identical, like 1, 2, 1, 2, 1, 2, the result is the maximum number of pairs, which is determined by combination math. For a single domino, no pairs exist, so the result is 0. By normalizing the dominoes and using a hash map, this method efficiently solves the problem for both small and large inputs. In this solution, we aim to count the number of equivalent domino pairs in the given list. Let's break down the code step by step. 1. Importing required module. We use defaultDict from the collections module to handle the frequency count of domino configurations efficiently without initializing keys manually. 2. Defining the method. The numberEquivDominoPairs function accepts a list of dominoes, where each domino is a pair of integers. 3. Using a dictionary for frequency counting, we initialize count as a defaultDict, int, to keep track of how many times each unique domino configuration, sorted tuple, appears. For iterating through each domino, for each domino, we sort the numbers in the domino to ensure they are order agnostic. For example, 2, 1, and 1, 2 will both be represented as 1, 2. Use this sorted tuple as a key in our count dictionary. 5. Counting equivalent pairs. For each domino, the number of equivalent pairs it can form is equal to the current count of the same key in the dictionary. We add this count to the result variable. 6. Updating the frequency. After updating the result, we increment the count for the current key by 1. 7. Returning the result. Finally, we return the result, which represents the total number of equivalent domino pairs. ### time and space complexity. Time complexity. The solution processes each domino exactly once, and the operations for sorting and dictionary lookups are O(1). Thus, the overall complexity is O(n), where n is the number of dominoes. Space complexity. We use a dictionary to store unique domino configurations, resulting in O(k) space, where k is the number of unique keys. This solution is efficient and concise, leveraging hashing and sorting to solve the problem in an optimal manner. This is the Java implementation of LeetCode problem number 1128, number of equivalent domino pairs. The logic mirrors the Python implementation. We use a hash map to store the frequency of each domino pair, formatted as an order-agnostic key, smallest value first. The result is increment by the count of equivalent pairs seen so far for each domino. Key differences include explicit type declarations and the use of Java-specific collections like hashmap. To solve this problem, we need to count the number of equivalent domino pairs. Let's start with a simple example. The input dominoes are 1, 2, 2, 1, 3, 4, 5, 6. First, we initialize two variables, a dictionary called count to store the frequency of each unique domino key, and result to keep track of the total number of pairs. Both start at 0. Now, we process each domino one by one. For the first domino, 1, 2, we sort it to get the key 1, 2. Since there are no existing keys in count, the result stays 0. We then update count to reflect that we've seen 1, 2 once. For the second domino, 2, 1, sorting it again gives the key 1, 2. This time, since the key already exists in count, we increment result by the current count of 1, 2, which is 1, bringing result to 1. We then update count to show that 1, 2 now has a frequency of 2. Proceeding to the third domino, 3, 4, sorting it gives 3, 4. Since this key doesn't yet exist in count, the result remains 1, and we update count to include 3, 4 with a frequency of 1. Finally, for the fourth domino, 5, 6, sorting gives 5, 6, which is also not in count, so the result stays 1, and we add 5, 6 to count with a frequency of 1. After processing all dominoes, the count dictionary looks like this: 1, 2, 2, 3, 4, 1, 5, 6, 1. The final value of result is 1, which means there is one pair of equivalent dominoes in this example. Now, let's examine another case where there are multiple pairs. The input dominoes are 1, 2, 2, 1, 1, 2, 2, 1. We start again by initializing count as an empty dictionary and result is 0. The process remains the same. We sort each domino to obtain a consistent key and update our count dictionary and result accordingly. For the first domino, 1, 2, sorting gives the key 1, 2. Since this key is not in count, result remains 0, and we add 1, 2 to count with a frequency of 1. Next, for the second domino, 2, 1, sorting again gives 1, 2. This time, the key already exists in count, so we add its current frequency, which is 1, to result, making result equal to 1. We then increment the frequency of 1, 2 in count to 2. For the third domino, 1, 2, sorting gives 1, 2. The key's frequency in count is now 2, so we add this value to result, bringing it to 3. We then update the frequency of 1, 2 to 3 in count. Finally, for the fourth domino, 2, 1, sorting again gives 1, 2. The current frequency of this key is 3, so we add 3 to result, making it 6. We then increment the frequency of 1, 2 to 4 in count. After processing all dominoes, the count dictionary is 1, 2, 4, and the final value of result is 6. This means there are 6 equivalent pairs of dominoes in this example. Now, let's look at a case where no equivalent pairs are present. The input dominoes are 1, 2, 3, 4, 5, 6. We initialize count as an empty dictionary and result is 0. For the first domino, 1, 2, sorting gives the key 1, 2. Since this key is not in count, result remains 0, and we add 1, 2 to count with a frequency of 1. For the second domino, 3, 4, sorting gives 3, 4. Again, this key is not in count, so result stays 0, and we add 3, 4 to count with a frequency of 1. Finally, for the third domino, 5, 6, sorting gives 5, 6. This key is also new, so result remains 0, and we add 5, 6 to count with a frequency of 1. After processing all dominoes, the count dictionary is 1, 2, 1, 3, 4, 1, 5, 6, 1, and the final value of result is 0. This means there are no equivalent pairs in this example. To analyze the time complexity of the given solution, let's start by examining the individual components. First, we iterate through the dominoes array using a for loop. Since we visit each domino exactly once, this operation takes n time, where n is the number of dominoes in the input. Next, for each domino represented as a pair, A, B, we sort the pair to ensure a consistent ordering. Sorting two elements is a constant time operation, O1, because the size of the pair is fixed. After sorting, we create a tuple from the sorted domino, which also requires O1 time. Finally, we use this tuple as a key in a dictionary to update its count. Accessing and updating elements in a dictionary is an average O1 operation, thanks to the efficiency of Python's hash table implementation. Combining these steps, the work done for each domino involves only constant time operations, apart from the initial loop, which scales linearly with n. Since each domino requires O1 operations, and there are n dominoes in total, the overall time complexity becomes O(n*(O1), which simplifies to O(n). Now, let's discuss the space complexity. The auxiliary space used by the solution primarily comes from the count dictionary. This dictionary stores the frequency of each unique domino key, where a key is represented as a tuple of two integers. In the worst-case scenario, all dominoes are unique, which means the dictionary will contain n keys. Each key requires O1 space, and with n keys, the total space used by the dictionary is O(n). Additionally, for each domino, we create a tuple using tuple sorted domino. However, these tuples are temporary and are discarded after use, so they do not contribute to the overall space complexity. As a result, the primary contributor to space usage is the count dictionary, making the total space complexity O(n). Besides the dictionary, other variables like the result variable and loop iterators use only O1 space. Therefore, the space complexity remains O(n). To compare, a naive or brute force approach to solving this problem would involve comparing every pair of dominoes using two nested loops. This approach would have a time complexity of O(n²), as each domino is compared with every other domino. In contrast, its space complexity would be O1, since no additional data structures are used. The optimized solution improves upon this by grouping equivalent dominoes using a dictionary. This reduces the time complexity to O(n), while introducing an O(n) space requirement for storing the dictionary. Overall, the optimized solution is significantly faster for larger inputs, making it much more practical. The best, average, and worst-case scenarios all maintain the same O(n) time complexity because the solution processes the input array linearly. However, the space complexity can vary based on the distribution of dominoes. In the best case, where all dominoes are equivalent, the dictionary contains only one key, minimizing space usage. In the average case, with a random distribution of dominoes, the space complexity depends on the number of unique keys, but it remains O(n) overall. In the worst case, where all dominoes are unique, the dictionary stores n keys, consuming O(n) space. Mathematically, the big O for time complexity is proven by noting that each domino undergoes constant time operations. With n dominoes, this results in O(n). Similarly, the space complexity stems from the dictionary, which can store up to n keys, each taking O(1) space, leading to O(n) in total. This optimized solution achieves a significant performance improvement over the naive approach, making it both time and space efficient. When solving this problem, there are several common mistakes to watch out for. First, it's critical to handle reversed pairs correctly. A domino pair like A-B is equivalent to B-A, so failing to account for this symmetry will lead to incorrect results. For example, if you treat 1, 2, and 2, 1 as distinct, you'll overcount or undercount pairs. Another common pitfall is relying on an inefficient brute force approach. Comparing all possible pairs using nested loops has a time complexity of O(n²), which quickly becomes too slow for large inputs, such as those with sizes around 10,000 or more. Additionally, not normalizing domino pairs can introduce unnecessary complexity. By consistently representing each pair as min A, B, max A, B, you eliminate duplicates and simplify comparisons. Lastly, it's important to consider constraints and edge cases. Scenarios like having only one domino, all dominoes being identical, or domino values at their minimum or maximum limits can easily cause runtime errors or inaccurate results if not handled properly. Another issue to consider is the unnecessary use of extra space. Adding intermediate data structures might seem helpful, but it can increase space complexity without actually improving the solution. Instead, focus on using minimal and efficient storage. Now, let's look at some key insights for interviews. Normalizing domino pairs is a fundamental step. By consistently storing pairs as min A, B, max A, B, you simplify your logic and reduce the chances of errors. To optimize further, using a hash map allows you to count normalized pairs efficiently, reducing time complexity to O(n). During an interview, it's also important to communicate your assumptions clearly. For example, explain how you're handling equivalent pairs and discuss how you've accounted for edge cases. This shows that you've thought about the problem holistically. Finally, be prepared to discuss specific edge scenarios, such as no valid pairs, having only a single domino, or all identical dominoes. These cases can often come up in interviews to test your thoroughness. This problem also connects to several related problems in LeetCode. For instance, problem 49, group anagrams, involves similar hashing and normalization concepts, where you group strings based on their equivalence. Problem 1288, remove covered intervals, uses sorting and normalization to simplify comparisons. Problem 1, 2sum, and problem 560, subarray sum equals k, both involve hash map lookups for efficient pair matching under constraints. As for alternative approaches, the hash map method is the most efficient, with a time complexity of O(n), though it requires additional space for storing counts. Another option is sorting combined with a two-pointer technique. While this approach simplifies the logic, its time complexity increases to O(n log n), which might be less ideal for very large inputs. Finally, there's the brute force approach, which is the simplest to implement but highly inefficient with its O(n² complexity, making it impractical for larger datasets. Each approach has its trade-offs, so it's important to choose the one that balances efficiency and clarity based on the context. Great job! We reviewed the problem, explored a brute force approach, and arrived at an optimal solution using hash maps. Remember, mastering these techniques will help you in interviews and real-world coding scenarios. Thanks for watching, like, subscribe, and keep practicing to level up your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!